Alright, so let me walk you through how to do a standard student's t-test and a z-test. And so the t-test, at least, I know most of you have probably done, and this is the standard statistical analysis that you've used pretty much since Bio 2010 and Bio 2011. Alright, so however, this is often used too often. In other words, this is used at times when it's not applicable. So the t-test is great for when your number of samples is less than 30, although it can work for samples over 30 as well. But in the right circumstances, if your data is correct and hits some assumptions, if you have more than 30 replicates, the z-test actually is more powerful. All right, so the t-test, again, when your sample is less than 30, this part is absolutely critical. It means you have to have one variable, two categories. So variable means you're changing one thing. Two categories means you have two groups. So really you're only comparing two different groups, control and the test group, and that's it. It allows you to do statistical analysis if you have unmatched parametric data. So matched, what does matched mean? So if you have paired data that's matched, that means it's the same individual. So examples of paired data would be if I am comparing eye drops, and I have control eye where I don't have drops, and I have a test eye where I do have drops, and assuming those two eyes have the same affliction or whatever you're trying to test, that would be paired data, or often called matched data. Another example would be a pre and post test. So if I gave a test to students, and then I gave that exact same test to students after a lecture or after doing something to help them learn, because I wanted to see if it did learn, that is paired or matched, because the same person, you have the before and you have the after. All right? So this actually, a t-test, will work for paired or unpaired, matched or unmatched. You also don't necessarily need equal variances, and I'll talk about this in a second. So, less than 30 samples, you only have two groups, one variable. It can be used for matched or unmatched, or equal or unequal variances. Alright, so the student's t-test assumes equal variances. So when you say the student's t-test, you're talking about equal variances. This is the most commonly used, but it's not always appropriate. And I'll show you how to just use a t-test where you're not assuming equal variances. And if you do that, you're going to be right way more frequently. And that's the t-test assuming unequal variances. So you do not require equal variances. This actually does just as well when the variances are equal. So pretty much when in doubt, you should always use the t-test that assumes unequal variances. So when I show you the t-test, I'll show you two ways of getting it. But one, if you open up the t-test functional argument, you'll see the different types of things you have to input for a t-test. You have to input your replicate data for array 1, so group 1, your replicate data for group 2, and then tails and type. All right. Tails we talked about already. This is it one-tailed, meaning your variance only goes in one direction, or is it two-tailed? So when in doubt, you're always going to use a two-tailed test. So for tails, you're just going to type 2. And then type, the reason I have this here is type is going to tell you what type of test you're looking at. So is it paired? And if it's paired, you're going to put 1. And again, I talked about what paired means. Right eye, left eye, for example. Two sample equal variance, you're going to put 2. But when in doubt, unless you have paired data, you're going to use two sample unequal variance, 3. So basically you're going to select your first group of data, your second group of data, tails 2, two-tailed test, type 3. That's almost always going to be your t-test options. All right? So before I get to z-test, let's go ahead and let's take a look at this, and let's complete this. I'm going to go ahead and make this a little bit larger so that hopefully you can see it better. Alright, so here's my two sets of data. Obviously I would need to have more information about this. Am I talking about this in millimeters, things like that? I would need units, but here's my data. And so within that data, I will have my average, and I will be able to make standard deviation, and I'll let you guys go ahead and do this because you know how to by now. But very simply, equals, start to type in the function. I want the average of this group of data. Once I have that, I can just slide this over and it'll take the average of the group above it. and I want the standard deviation, so I need to type equals to get it to give me that option. Standard deviation of the sample, because we don't have the entire population, and do not include your average as a data point. And so I can time that over, move that over. And if I want to look at significant digits, I can just select these cells, and I can go to my data frame here. Actually, it's on home, sorry. And you can see here, this is going to give you the ability to increase the number of decimal places or decrease. So I can just kind of decrease those decimal places until I have something reasonable. 2 decimal places there. There's my average and standard deviation. So now, to do the t-test, I'm going to simply type in the function for equals t-test. And you can see here those values that I have to input that I just showed you. Array 1 is my group 1 data, array 2 is my group 2 data, tails, and type. And so my group 1 data is this. Do not use the average and standard deviation. They are not replicates. Just choose your replicates, comma, second set of data, comma. This is two-tailed. And you can see here it kind of shows you the options. So when in doubt, you always want two-tailed because the lengths can vary in both directions from the average. And I don't know if my variances are equal or not, so when in doubt, I'm going to always use 3. So your data, comma 2, comma 3. That is going to give you your t-test value. And in this case, we see that our t-test is 0.3999. So do not forget that you then need to go back to the original purpose of this experiment. So if this experiment was to see if there was a difference between the lengths of periwinkles on the lower shore or the northern shore or the upper shore, basically this is telling us that I cannot reject the null hypothesis. There is no statistically significant difference between those lengths. So maybe I was trying to see if some pollution on the lower shore was statistically making these periwinkles grow smaller. And yes, the average shows a little bit smaller, but because of the data, the variation, and so forth, this is not statistically significant. Therefore, I cannot conclude that the pollution is causing the periwinkles at the lower shore to grow smaller. My null hypothesis is not rejected. You always need to bring that analysis back full circle to the original purpose of the experiment. All right, so let's go back to the z-test now. This is for unmatched data, so non-paired data. This is, again, one variable, only 2 categories, so 2 groups. Unmatched parametric data. Data has to be parametric data. All right, I talked about matched versus unmatched already. This is actually a more powerful test than the t-test, but you have to have at least 30 observations. All right, and in fact, this is powerful enough that every once in a while this can even be used for non-parametric data, as long as, again, you have those large data numbers. The key here, though, is that the variances have to be similar for the 2 samples. So you cannot use this unless the variances are similar. So how do you determine if the variances are similar enough? Well, to do that, we have to do an f-test. So what this means is in order to do a z-test, we have to do the f-test, testing for similar variances first. All right, so how do we do that? The f-test simply compares the variances of the 2 populations. You can compare your f calculated to the f critical. All right, and these tables that you have are in your reader, and I'll also have them on these slides here, and I think you have them on the student slides that I handed out. So, first thing to do is to get the f calculated. The f calculated is simply the variance of the sample with larger variance divided by the variance with smaller variance. All right, so let's take a look at this and do this together as we go. So here I have another set of data, again from periwinkles, but now I have 30 data points. So that's why I'm going to have to scroll up and down here. But I have 30 data points now. And so I can go back through here, I can get my average, I can get my standard deviation. You guys know how to do this by now. But importantly, I can also get my variance. And I need to get my variance in order to do my f-test to figure out if I can do a z-test for this. So simply type equals variance, and just like standard deviation, we don't have the whole population, so it has to be variance S of sample. And so I'm just going to get the variance of this whole set of data here. And then I have the variance of my other set of data as well. So to get my F calculated, basically what I need to do is take the higher variance divided by the lower variance. That gives me my ratio. Then I'm going to need to compare this. So basically I need to figure out if this is too high. Is that difference in the variance too much, or is it okay? And in order to do that, I need to jump back over here. So I need to use the F critical value. So this is straight from the table, all right? And what you have to do is remember your degrees of freedom. Degrees of freedom means your replicates number. In this case, I have 30 minus 1. So my degrees of freedom for this data set would be 29. 30 replicates minus 1. However, as you'll see in the table, there isn't always the exact number. So we're going to always want to err on the side of caution. Right? So in this case, you're going to round up. All right, so let's go on, and you'll see here. So variance. So the variance for number 1, the variance for number 2, this is just the one with more variance, the one with less variance, right? Divided the higher variance by the lower variance. And so I had, my degrees of freedom is 19, but I don't see a 19 here, so I'm going to round up to 20. On the other hand, for this one I have 19, so again, my 20 and 19, what I end up with is a value of 2.51. Right? So that value of 2.51 is my F critical. And as long as my calculated ratio of the variances, as long as F calculated is less than F critical, I do not reject the null hypothesis. And if I don't reject the null hypothesis, it means that my variances are close enough. Right, so let's go back over here. My F calculated was 1.14, sorry. My F critical was 2.5. Basically, what this means is that this is close enough. My variances are close enough. So if F calc is less than F critical, then variances are close enough. And so now I can do my z-test, and once that's true, the z-test is easy. So I'm just going to go to my data analysis. I'm going to look for the z-test to sample for means. And so now I just need to select my data for group 1. That's input 1 range. But what I do have to remember though is variable 1 is the one that had the higher variance. So actually I want to use this as variable 1 because it was the one with higher variance. And so this one becomes variable 2. So again, that is important. You have to remember that your F calculated was V1, the higher variance, over V2. And so that is going to determine which one is my variable 1, which one's variable 2. Variable 1 is always the one with the higher variance. Right? And so then I'm going to put in the variance. So the variance for variable 1 was 4.1. I'll just kind of round to that 1 decimal point. Variance 2 was 3.6, round to that same decimal point. And then my output is where I want to make this data go, and it's going to be a table, so I need to give it some space. And then there is my v-test, or z-test, sorry. So the z-test, here's one-tail versus two-tail. This is two-tailed again, and when in doubt, it's always two-tailed. All right, so the p for my two-tailed test is 0.00015. This means that this data is significantly different from each other. I reject the null hypothesis that they're the same. So now I need to go back and figure out what that means. Well, in order to do that, I really need my averages. I need to figure out what's different about them. So here I see that the average on the lower shore is 5.54. The average on the upper shore is 7.47. So I can now say that the lower shore periwinkles are significantly shorter than the upper shore. And you have to, again, complete that circle. Don't just say they're different. How are they different? Well, the lower shore ones are significantly shorter than the upper ones. And so that's how to do a z-test. Remember, you have to do the F calc and F critical. You have to compare the F test to make sure the variances are close enough. then you